Okay, so in this video, what we're going to do is we're going to talk about something that kind of sounds scary, but actually is really, really straightforward. It's called the reaction quotient, and it's Q. So, what the heck is a reaction quotient? Well, we use the reaction quotient when the system is not at equilibrium. So, what is the reaction quotient? Well, so when do we use the reaction quotient? Well, we use it for when the system is not at equilibrium. And whenever a system, and by system I mean a reaction, is not at equilibrium, it will do whatever it can to get back to equilibrium. So that's the point. Your goal if you're a reaction and you're an equilibrium reaction is you want to get back to equilibrium if you're not at equilibrium. So if we take a look at our basic AA, BB, CC, DD thing that we saw originally, this may look shockingly familiar because if you remember in the previous video we said K is equal to, and we always take the products concentrations raised to their coefficients, and that's both the products raised to their coefficients, times the reactant, or divided by the reactant raised to their coefficients, right? And if you take a look at what I've just been writing out right here, compared to this, it's exactly the same thing, which begs the question, are Q and K the same? And the answer to that is no, because what we put in here for our C, D, A, and B are concentrations in both cases. But the concentration we put in C, D, A, and B when we're dealing with our reaction quotient are typically our initial concentrations. So we can take any reaction and throw stuff into like a container together and then watch them react. And for example, if all I have are reactants, then when I throw them in there, the reaction is going to probably shift towards the products, and we're going to have different amounts at the end in our K of our different quantities than we do at our beginning. So we could potentially, if I gave you values of C, D, A, and B, you could theoretically have the exact same values that put this at equilibrium. So our Q could be equal to our K, and therefore we'd say it's at equilibrium, but very unlikely that our Q is equal to K. So what does Q mean? Well, if our Q is not the same as our K, it simply means that we're not at equilibrium. But what I want to point out to you here is this. In both our Q and our K, aren't our products over our reactants? Now, why that matter? And I'm going to just write concentration of products over a concentration of reactants for both K and Q. The reason I'm doing it this way as opposed to putting C to the C, D to the D is because it's easier to view this. But wouldn't you agree with me that our products are over our reactants? So in my equilibrium constant, my K value, whatever number they give me for my K, that's the ratio of my products over my reactants. Similarly, the ratio of my products over my reactants for Q is for Q. Now, if I compare these two and I have in my Q value, my Q is less than K, what that means is that if you take a look, that if this Q value is less than my K value, that must mean that my Q has less products than it does reactants. In other words, what we're saying is that the products are too little and the reactants are too big. And every reaction always moves to equilibrium, so that means that the reactants, since we don't have enough products, we're going to move towards the products to get to equilibrium. Now, if our Q is equal to K, it means we're at equilibrium. Now, what about the opposite? What if my Q is bigger than my K? In other words, my products in my Q expression, I have too many products. Well, if I have too many products, wouldn't I shift back towards the reactants? Yeah? So if I have too many reactants, and I'm sorry, too little reactants and too much product, in order to move to equilibrium, we're going to have to shift back towards the reactant side. Now, that can seem a little bit confusing, but I'm going to show you this, and this is actually a pretty easy way of doing this. So what I want you to do is I want you to pretend that we have a number line, and we're going to write Q and K, depending on whichever one is bigger. So if my Q is greater than my K, right? If my Q is greater than, I'm sorry. So this is an easy way to kind of figure out which direction the reaction will shift, and this is important in all of our problems, which direction the reaction. So it's really important to know which direction a reaction will shift to get back to K. Because remember, that's the important thing. Every reaction wants to get back to the perfect ratio that the K states. So if our Q is less than our K, what we're going to do is we're going to make a number line, right? And what we'll do is we'll put our Q versus our K depending on which is bigger. Now in this case here, our Q is smaller than our K, so we're going to put it to the left on the number line. And which direction will the reaction shift to get to the K? Well, it'll have to shift to the right. So that means that we do not have enough products and we'll have to shift to the right. Well, let's just say that we have a Q that's bigger than our K. We'll put it on our number line again. If our Q is bigger than our K, which direction will we have to shift? We'll have to shift to the left to get back to the perfect K. That means that we had too much products to begin with. So another way of just looking at this is this. Whenever they give us concentrations of the stuff in our reaction, we don't know whether or not we're at equilibrium or not. But we can write the equilibrium expression, or the law of mass action. That's our K expression, right? And then we can instead just change K to Q and solve for what we have currently. Now, depending on whether our Q is bigger than our K or our Q is less than our K, will determine which direction our reaction will have to shift to get back to equilibrium. And remember, that's the most important thing. Our reactions want to shift to get back to equilibrium. So if you remember this table over here, or the number line, it'll actually kind of remind you which direction we have to shift once you solve for our K. And then let me say it one more time, even though I've been a little redundant for this. The only difference between Q and K is that Q are some numbers they're giving us that are not necessarily at equilibrium. So we solve for the numbers they give us and we compare it to the K, which they must give us in the problem, to determine whether or not our reaction is going to shift one direction or another. I'll see you in the next video. Hope this has helped.